Typical, I wrote the title in abstract before writing the talk, so I think maybe I strayed a little bit. What I want to do, my goal today is just to show you what I think is a very pretty theorem and a very pretty proof. So let's start with Erdős-Corrado. This is a classical theorem in combinatorial set theory, and I'm going to give you the simplest version. So here's the statement. I'm going to let n be greater than or equal to twice k, and I'm going to look at a set of size n, numbers 1 through n will do, and I'm going to look at all of the k subsets of this set. And then I want to select a family of these sets. And the condition that I have on this family is I want my family to be intersecting. That means whenever I take two sets in F, they have non-empty intersection. And the question is, well, how large can F be? And if you were to sit down, kind of think about this, the first thing you would probably try would be to fix one element, say 1, and then look at all of the k subsets that contain 1. And that gives you a good first guess. And in fact, that's the best you can possibly do. So the theorem says the size of F is bounded above by n minus 1 choose k minus 1. It's exactly the number of sets that contain 1. And if you meet the bound, then you are exactly the family of sets on a point. So is there anybody who hasn't seen this theorem before? Show of hands. Okay, good. Perfect. So this is...
we did this in the class. Sorry, but what is
sure.
Right? What is nothing?
F is the set of... Sorry, yeah. Now my writing is terrible, so just complain if you can't read anything. F is the set of sets on a point. So this is, as I mentioned, the simplest version of this theorem. So in fact, even though I've cited Erdős-Corrado from 1961, this was something that was known at the time that this paper was published. What Erdős-Corrado prove is something stronger. They prove that a similar statement holds if you change intersecting to t-intersecting. So now I don't want my sets to just intersect, I want them to intersect in at least t points. And you have a similar sort of statement, but I'm not going to talk about that at all. In fact, I'm hardly going to talk about this theorem at all. I just write it down to give you an idea of what kind of a statement we're looking at. And so this theorem sort of started or generated a huge volume of research. People were interested in finding different solutions to this problem than was originally given, different proofs, kind of extending that result in various ways when looking at families of sets, and sort of extending this theorem and considering different objects other than sets. So we can kind of write down what we might call an Erdős-Corrado or EKR-type theorem. So what do I mean? I have, kind of wrote this down. So given a suitably restricted set of objects, which we'll call O, an intersecting family F of objects in O has the size of F bounded above by B, and if equality holds, then F is canonical. So here there's a whole bunch of weasel words, and I'm not actually going to define them. I just write this down because this is sort of the pattern you want to have in your mind if you're kind of thinking about identifying these theorems. So what do I mean? So by kind of set of objects, maybe I'm looking at subsets of an n set with maybe a given constraint, like n is at least 2k. I have some notion of what intersecting means. For subsets, this is obvious. For other objects, maybe it isn't. From this notion of intersecting, I have some obvious large intersecting families. The size of those intersecting families is best possible. That gives me a bound. And it gives me a characterization. So this theorem has kind of two main parts, a bound and a characterization. So what types of objects can we prove an EKR-type theorem for? Well, there's quite a few. I'll write down some. So I need to find... So in 1977, a version of this theorem was proved for subspaces of a finite vector space. So now I'm interested in looking at a vector space of dimension n over some finite field of order q. I'm going to look at all of the subspaces with dimension k, and I want to pick an intersecting family. Of course, I'm going to need to change my notion of intersecting because every two subspaces intersect. I'm going to say that two subspaces are intersecting if they share a line. And now you get a sort of obvious upper bound. The obvious upper bound comes from taking a family of subspaces that contain a given fixed line. And that's the best you can do. So we also have a similar result for strings of some fixed length. So now say I have an alphabet with q symbols, and I'm going to look at all of the strings I can make with that alphabet of length n. I'll say two strings intersect if they agree on one of their positions. And now the question is, how large can an intersecting family be? And the answer is, well, you pick a position and you pick a symbol and you look at all of the strings that have that symbol in that position. And that gives you your answer. And finally, the theorem I'm going to talk about today is for permutations, in particular elements of the symmetric group. So this is due to an array of people. So Deza and Frankel proved the bound part of this theorem in 1977, and there was a long gap before the characterization was proved. And it was proved independently by Cameron and Koo, and LaRose and Malvenuto in 2003, 2004, respectively. So the statement, again, by now is familiar. I have an intersecting family in Sn. What does it mean to be an intersecting family? Well, I'll say that two permutations, say sigma and tau, intersect if and only if there is some I on which they agree. This is straightforward. Then, again, I have an upper bound. The size of f is at most n minus 1 factorial. And how do we come up with this bound? Well, notice that any point stabilizer is going to give me an intersecting family. And the characterization says if I have an intersecting family of size n minus 1 factorial, then I must be some coset of some point stabilizer. These are all of the maximum intersecting families. So our goal is to prove this theorem, which we might be able to do. And the proof I'm going to show you isn't due to Cameron and Koo or to Rose and Malvenuto, but we're going to follow Godsell and Marr. From 2007. And they've given an algebraic proof. And so what I'll show you is different than what you will see in that paper. We're going to sort of use a bit of a cheat and make some improvement on that presentation of this proof. Okay, so how is this going to work? So our main object is the derangement graph. So what is the derangement graph? So a derangement is a fixed point free permutation. I'm going to let Dn be the set of derangements in the symmetric group S sub n. So for example, for n is equal to 3, the symmetric group, identity element, permutation that swaps 1 and 2, permutation that swaps 1 and 3, permutation that swaps 2 and 3, and then the cycle 1, 2, 3, and its reverse 1, 3, 2. What are the derangements in this group? Well, the identity has 3 fixed points. Each of my transpositions have 1 fixed point, and these guys are fixed point free. So I get exactly 1, 2, 3, and 1, 3, 2. So now I want to define a graph. So what I'm going to do is I'm going to let my derangement graph be xn. This is going to be x Sn dn. So this means I'm constructing a Cayley graph for the group S sub n, and my connection set is the group D sub n. So this means vertices is Sn, and sigma is adjacent to tau, if and only if sigma tau inverse is a derangement. So again, going back to our example, x3 is not particularly interesting, but these graphs get very large very quickly. Oops, sorry, no, should be there. Yeah. But I get 2 triangles. So you'll notice that you can check for yourself every time I have an edge. If I look at sigma tau inverse, it's fixed point free. So if you're not familiar with Cayley graphs, these things can be defined more generally. Usually for, in this notation, I have some group G and some connection set C. And then I have, this is exactly my adjacency condition. So 2 group elements are adjacent if and only if this product of one times the inverse of the other is in my connection set. But of course, this isn't a symmetric relation. So if I just allow C to be some arbitrary subset, it's possible that I have a graph that has, say, loops. So my loop is going to correspond to an identity element, and it's possible that it'll have arcs. So say from some G to some H. And the way we get around that typically, if we want to work with simple graphs, is make sure the identity element isn't part of our connection set, and insist that our connection set is inverse closed. So that gives me all of my reverse arcs. And in this case, that's true. So if you look at the set of derangements, it shouldn't be too hard to convince yourself that that set is both inverse closed and doesn't contain the identity. So what can we say about x sub n? Some basic properties. First off, it's a Cayley graph, which means it's vertex transitive. So its automorphism group acts transitively on its vertices.
So, isn't this relation sort of symmetric? If sigma and tau if sigma and tau inverse is in Dn?
Yes. So I've been a little bit lazy. So if I was kind of to be not so lazy, I would kind of define arcs. But because I'm not looking at.
Does it make sense to have one arc and an inverse, or shouldn't you just think about one and then?
Yeah. So typically when we talk about graphs, we tend to think about edges as being undirected. But if we want to talk about directed graphs, you have these directed arcs, and then the convention is if you have two reverse arcs, you can consider it being the same as some undirected edge. So you're.
Okay. Yeah, but I mean here sort of it's like automatic.
Yes,
with this relation.
It is. That's just the point I was making. Okay, so x sub n is vertex transitive, which is nice. Of course, it's going to be regular. So that means every vertex is going to have the same degree, and the degree will be equal to the size of my set of derangements. And now if you remember from probably your first enumeration course, well, if you don't, that's fine. We have a nice recursion for these numbers. D sub n, in particular, n minus 1 times dn minus 1 plus dn minus 2. Another important fact is that xn is connected. Except I just drew a non-connected graph. It's connected provided n is at least 4. But n is equal to 4 was too large to draw on the board in a sensible way. And finally, so this will come back later, xn is what's called a normal Cayley graph. So what does it mean for a Cayley graph to be normal? It just means that if I look at my connection set, the connection set is a union of conjugacy classes of elements of my group. So how are we going to deploy this object? Well, I can rewrite the theorem I'm trying to prove, my EKR for permutations, entirely in terms of this graph. So now our theorem is. Yeah, go ahead. Connection set is just this set of group elements that gives you your arcs, right? So yeah, in this case it's dn. Yeah. So now our theorem becomes the independence number of this graph x sub n is equal to n minus 1 factorial, and the maximum cocleeks are exactly the cosets of point stabilizers. So why is this true? Well, so if you look at two permutations.
Maybe you want to explain the count like cocleeks or something.
Okay, sorry. Yeah, so alpha. So okay, so a cocleek is an independent set is a subset of vertices in your graph, so that none of them are connected by any edges. So, for example, take any vertex here and any vertex here. That gives you an independent set or a cocleek. This notation alpha of some graph is just the size of a maximum cocleek. So notice that I have two of my permutations, sigma and tau, are adjacent, if and only if sigma tau inverse has no fixed points. or in the opposite direction, I have no edge here if and only if I have some fixed point. Well, a fixed point of sigma tau inverse corresponds exactly to some element that's mapped onto by both permutations in the same way, right? So so sigma tau inverse has a fixed point if and only if there exists some I, so that sigma I equals tau I. Okay, so we've taken our problem and rewritten it in different language. What good is that? Well, we have tools for working with independent sets in graphs. And I'm going to show you two. The first tool, the first tool is due to Delsart originally around the 1970s. Did I write that down? Nope, I didn't. So this is called, some places, the clique co-clique bound. Co-clique is an independent set. Inversely, a clique is a set of vertices so that every pair is connected by an edge. So what does this theorem say? If X is vertex transitive, then omega x times alpha x is at most the size of x, and if equality holds, we get some extra information. If equality holds, then if I pick any maximum independent set and any maximum clique, they must intersect in exactly one vertex. Well, obviously they can't intersect in more than one vertex, otherwise you would have two contradictions. But there's no reason, given an arbitrary graph, why some maximum clique and maximum co-clique should intersect. And actually we can give a nice short proof of this fact. Yeah.
Can I ask you?
Sure. Yeah.
So where vertex transitive is used in this theorem?
Right. So I'm going to show you a proof. Except I'm going to change vertex transitive to Cayley graph. So you'll see kind of how this works for Cayley graphs. For vertex transitive graphs, it's a little more complicated, but not too bad. So I'm going to change. Vertex transitive to Cayley graph, and if I do that, then suppose S is independent, then S inverse is independent. It's not too difficult to see. And now suppose I have two vertices, X and Y in my graph, that are adjacent to each other. So S is just a set of group elements. So by S inverse, I just mean the set that you get by replacing every group element with its inverse. Yeah, thanks. So I'm going to suppose I have two adjacent vertices, and I'm going to consider some element Z of the translates, or the intersection of the translates, S inverse X and S inverse Y. So this means I can write Z as some S inverse times X and some, say, T inverse times Y, where S inverse and T inverse are elements of my set S inverse. And now I just rearrange this. So I get XY inverse is equal to S T inverse, and now I'm done. So why am I done? I know at least one of you knows, because you're in my algebraic graph theory course. So I'm done because I assumed XY was an edge, so XY inverse is in the connection set. but I assumed that my set S is independent, which means I can't have ST inverse in the connection set. So I get my contradiction. And now if I want to show that I must get this intersection property, or well, actually to prove the bound, let's not get ahead of ourselves. So to prove the bound, all I'm going to do is take S to be some maximum independent set and take C to be some maximum clique, and then just look at this set of translates. So S max independent set, C max clique, and I just look at the set of translates S inverse X such that X is an element of C. Well, I've just proved that all of these sets are distinct, so they must give me a partial partition of the elements of my group, and the size of or the number of elements in that partition is the size of C times the size of S. So I get my bound. And in fact, the extra bit of information falls out immediately as well. If I suppose I get equality, then this construction works for any independent set and any clique. So I can get this nice partition of my group using an independent set, and now my clique must intersect every one of those parts in exactly one location. Because I wrote proof on the board, make me feel better if I write a little square. So how do we deploy this to prove our theorem? Well, we have candidates for independent sets. We also have candidates for large cliques. In fact, large cliques are easier to find than the large independent set. Or it's easier to prove that a large clique is maximum than it is to prove that a large co-clique is maximum. So I'm going to consider a clique C in X sub n. So what is my clique? My clique is a set of group elements, a set of permutations. And now what I'm going to do is I'm going to write every permutation in the form 1 to n, and then sigma of 1, sigma of 2, sigma of n, except I'm going to kill the first row. I don't care about the first row. So if I do this, I get sigma I of 1, sigma 1 of 1, sigma 1 of 2, through to sigma 1 of n, and I can keep listing these: sigma 2 of 1, sigma 2 of 2, sigma 2 of n, etc., through to, say, sigma I of 1, through sigma I of n. I noticed two special things about this grid of numbers that I've just written down. First off, every row is a permutation of 1 through n. And second of all, these guys are a clique, which means if I look at any two rows,
They're distinct.
Well, they're definitely distinct, but they also can't intersect in any of their entries. So what is this object I've written on the board?
What is what?
So what is this thing, more commonly known as?
Latin square.
Right, it's a Latin rectangle. Right.
Yeah.
So my cliques are exactly Latin rectangles. How large can a Latin rectangle be? Well, square. And I have Latin squares for every value n I want to consider. So I know that omega of xn is equal to n. And now by my clique-co-clique bound, alpha of xn is at most n minus 1 factorial. And of course we have examples of co-cliques with size n minus 1 factorial. So this proves the bound. So that was fun. Let's do it again. So that was one tool. Yeah, sure. Oh, sorry, this is just some set of indices. I just sort of.
What was the conditions on the sigmas?
These are just permutations that are in a clique in my graph. So there's an edge between every pair of the permutations here, which means that they're sort of separated by a derangement, if you like. And because they're separated by a derangement, they can't have. You can't see the same value in any column. Yeah. So this is sort of the easiest proof, I think, of the bound in this theorem. And this proof, you'll kind of see this in a couple of the papers that I mentioned, even though they don't give a full algebraic proof of the the characterization. Usually they kind of start with this, this observation because it kind of falls out quite nicely. So the way we're going to get the characterization is we're actually going to use a different bound on the size of a Koch leak. So we're going to use what's called Hoffman's ratio bound. So Hoffman's ratio bound is a bound on the size of an independent set in a graph that uses its eigenvalues. To catch up to myself. So this is another very useful result. And it says if I have a k-regular graph, so this is just a graph where the degree of every vertex is equal to k, and I look at the eigenvalues of my graph, and the least one happens to be tau, then if I have a maximum independent set S, the size of S is bounded above by this function involving the size of my graph, its valency, and the least eigenvalue. And sort of the most useful part of this theorem, at least for us, is the second bit. So the second bit says if I achieve equality, then I get eigenvectors. And these are going to be very useful.
Yes is the characteristic vector.
Oh, sorry, yeah, thank you. Yeah, so here I just mean, so this vector v sub s is a 0, 1 vector. The zeros correspond to the vertices not in my set S, and the ones correspond to the vertices that are in my set S. This is the characteristic vector. Thank you. And 1 hat is the vector with all entries equal to 1. So let's again, yeah, let's prove this theorem. Why not? So I'm going to let A be the adjacency matrix of my graph. So just for those of you who haven't seen this before, I guess B is a terrible idea. So x1 through xn. So I have this n by n matrix with entries 0 and 1, and I index the columns and the rows by the vertices of my graph, and I put a value 1 if the corresponding vertices are adjacent. So this is going to be a 0, 1 matrix. 0, 1 matrix with 0 diagonal. It's going to be symmetric because we're working with loopless, undirected graphs. So I have this nice symmetric matrix. All of its eigenvalues are real, and in particular, I can talk about the least eigenvalue without fear of contradiction. Okay, so I'm going to let this be my adjacency matrix, and I'm going to consider the matrix M. M is the adjacency matrix minus tau times the identity matrix, so the corresponding dimensions, minus k minus tau on the size of x times the all ones matrix J, again of the corresponding dimensions. So x is k-regular. That implies that 1 is an eigenvector for this matrix A. And it's also going to be an eigenvector for this matrix M. So what happens when I multiply M times 1? Well, here I get the size of x times the all ones vector. So this gives me k minus tau times the all ones vector. And here I get just tau times the L1's vector, and here I get k times the L1's vector. When you add those all up, you get 0. So I have that, this implies that 1 is a 0 eigenvector of M. And now what about any other eigenvector of my graph X? So if Z is any other eigenvector, oh well, here I should say that the valency of your regular graph is an eigenvalue with multiplicity 1. So any other eigenvector corresponds to a different eigenvalue. So now what happens when I multiply M times Z? Well, I'm going to get, so if Z is, say, a theta eigenvector, I'll get theta times Z when I multiply by A, and I'll get negative tau times Z when I multiply by the identity. And then when I multiply by the all-ones matrix, I'm just going to get 0, because the eigenvector Z is going to be orthogonal to any eigenvector from a different eigenspace, in particular the all-ones vector. So this is giving me the eigenvalues of this matrix M. In particular, because I chose tau to be the least eigenvalue of this matrix, or of my graph, of the matrix A, I know that all of the eigenvalues of M are non-negative, so it's positive semi-definite. And now we look at a characteristic vector of a maximum co-clique. We'll say S is a maximum co-clique. V of S, its characteristic vector. And I've properly lost my place. Oh, there we are. So I notice that by definition, Vs transpose times A times Vs gives me 0. So this takes a moment to realize, but sort of it's worth thinking about for a second. So now M positive semi-definite implies that if I use this same vector V sub S and multiply by M in the same way, I get something that's non-negative. And this is just going to be equal to negative tau times the size of S minus k minus tau on x times size of S squared. And now rearranging everything, you get exactly this bound. And the rest follows pretty easily. So if you kind of, again, kind of focusing on this matrix, you can try, you can simply try this as try multiplying A times this vector, and you'll see that it comes out to be a tau eigenvector. So I'll claim victory there, even though I haven't shown you everything. So something to notice. I already know what the independence number of my graph xn is. It's n minus 1 factorial, which is the size of x divided by n. So if it just happens that tau is equal to negative dn on n minus 1, then we get equality in the ratio bound. Which means we get this nice additional fact about our eigenvectors. Okay, so now it's just down to work out what the eigenvalues are. And luckily, because I have a normal Cayley graph, I can write these down explicitly. So we have this very nice theorem that tells us exactly what the eigenvalues are. But of course we have a problem, because just because you know exactly what something is doesn't mean you can do anything useful with it. So in order to say figure out what the least eigenvalue is, I need to sort of have some theory that tells me which characters are giving me my least eigenvalue. And it's not really obvious from a group, not all the time at least, what those characters are and which eigenvalues each character is giving you. So I mentioned at the top that this talk would involve some cheating, and now I'm going to cheat. So when Cameron and Koo published their proof of this theorem initially, they noticed this fact that so they'd used the clique-co-clique bound to get the bound part of the theorem, and then to get the characterization they had to do some finagling. And they said, well, it would be much nicer if we could just apply the ratio bound. And they sort of noted that, well, because we know what the size of these co-cliques are, this bound kind of is telling us that, morally at least, this should be the least eigenvalue of our graph. And they inspired Renteln to prove this fact. So in 2007, I published a paper which says a bunch of nice things about the eigenvalues of this derangement graph, but for us, we just need to know that the least eigenvalue of xn is negative dn on n minus 1 with multiplicity n minus 1 squared. So now we're off to the races. We have equality in the ratio bound, and we can try to use the fact that I'm pointing at the wrong thing. We can now use the fact that we get eigenvectors as well to try to derive some characterization on the maximum co-cliques. So I'm going to let S sub ij be the set of permutations in Sn that map I to j. So these are exactly my canonical co-cliques. And I'm going to let V sub ij be the characteristic vector of S sub ij. So our ratio bound tells us that for each I and j between 1 and n, the vector Vij minus 1 on n times the all ones vector is a tau eigenvector for xn. Now what I want to do is I want to find a basis for the tau eigenspace just using these vectors. And so you get a nice exercise for your linear algebra students. Here's a set of vectors. Show that it is linearly independent. I think I'm going to skip some of the details. Like I said, this is for your...
That's in R to the n factorial.
Yes, yeah. Yeah, these vectors are quite large. So to prove this, I'm going to let ij be less than or equal to I prime j prime if and only if I is strictly less than I prime, or I is equal to I prime and j is less than or equal to j prime. So this gives me just an ordering of these vectors. And instead of these vectors, I'm going to work with just the Vij's. So I'm going to let H be the matrix whose columns are the Vij's ordered according to this and stopping at n minus 1. So I have this matrix. I want to show these vectors are linearly independent. So what I'm going to do is I'm going to show that H transpose H is invertible. Actually, I should probably start writing over here. And to show that my matrix H transpose H is invertible, I'm going to figure out what its eigenvalues are. So I'm going to let Kn n minus 1. I can only use n minus 1. So yeah, we'll just n minus 1. So Kn minus 1 is the matrix Jn minus 1 minus In minus 1. So this is the adjacency matrix of the complete graph on n minus 1 vertices. So note that H transpose H is equal to n minus 1 factorial times I sub n minus 1 squared plus n minus 2 factorial times Kn minus 1 Kronecker product Kn minus 1. So again, this is nothing particularly deep. It's just a matter of looking at the inner products of these vectors Vij and observing that that's exactly what you expect. And now, of course, I know the eigenvalues of these matrices, and they tell me that the eigenvalues of this matrix are n minus 1, n minus 2, and minus 1. So the eigenvalues of Kn minus 1, Kronecker, Kn minus 1 are the products of n minus 2 and minus 1, so n minus 2 squared, negative n minus 2, and 1. And then I simply plug all those values into this nice sum, because any eigenvector of this matrix is also an eigenvector of that matrix. That gives me all the eigenvectors of H transpose H. And I just verify that no matter which eigenvector of Kn minus 1 cross Kn minus 1 that I choose, I get some value that's not 0. This is, again, straightforward. So that tells me that this set is linearly independent. And to see that this set is linearly independent, you now notice that the all ones vector isn't in the span of those vectors. And that finishes the proof. But like I say, so some details needed. So now I have a basis for the tau eigenspace. What am I going to do with it? So I'm going to take M to be the matrix whose columns are the Vij in any order you like. So now I'm looking at all of the vectors Vij from ij from 1 to n. So I'm getting all of these guys plus some more. You can use the same ordering, it's just not going to matter. So what do I know about the matrix M? So first off, notice that if I look at M times the all ones vector, what do I get? Well, the rows of my matrix M correspond to, so here's my matrix. Up here I have these vectors Vij, and my rows are all indexed by permutations. And as I look across, I'm seeing, if you like, a characteristic vector for this permutation in terms of these Vij's. So I'm getting exactly a 1 when this permutation maps I to j, and a 0 otherwise. So what is M times the all ones vector? Well, it's just going to be n times the all ones vector. I have constant row sums. What this tells me that the all ones vector is in the column space of M, as are all of these Vij's. So the tau eigenspace is in the column space of this matrix. So the tau eigenspace is contained in the column space of M. Okay. So now that I know that the tau eigenspace is contained in the column space of my matrix, that means whenever I have an eigenvector, so Z is a tau eigenvector, implies there exists X such that M times X is equal to Z. And now I've changed all of the notation, so I'm going to confuse myself every time I look at my notes, which is excellent. Right. Okay, so now let's go back to Hoffman's ratio bound. So suppose I have some maximum co-clique. We'll call it S. So suppose S is a max co-clique in Xn. This implies there exists some x such that m times x is equal to v sub s, my characteristic vector. So now let's do something really strange. So now I'm going to let P be a polytope. So P is going to be the convex hull of the vectors m sub sigma, such that sigma is in Sn. So here, by this notation m sub sigma, I just mean the sigma row of my matrix. So I'm just taking the rows of this matrix, taking their convex hull. That gives me a polytope. So something interesting about polytopes, something nice about polytopes. So for any vector y, if I look at the set of these vertices, so that my sub sigma is maximum, or if I look at the set of these vertices such that my sub sigma is minimum, these are both faces of P. Well, what's our context? I have some vector v sub s. It's expressed as m times x. So what are the maximum and minimum elements of mx? Well, they're 0 and 1. They're exactly the permutations that are in my co-clique and the permutations that are not in my co-clique. So those are going to give me faces of this polytope. Now that's extremely useful, because even though you don't recognize it yet, or perhaps you don't recognize it yet, you know exactly what this polytope is. So this is what's called the Birkhoff Polytope. So this is the polytope that you get if you look at the perfect matchings of the complete graph KNN. So what do I mean? I mean take a perfect matching of KNN, take the characteristic vector of that matching, by which I mean the characteristic vector according to the edges that it contains or doesn't contain. Then if I take the convex hull of all of these characteristic vectors, I get a nice polytope which has a nice description. And in fact, you can see very easily that it's exactly going to be this polytope, because we already noticed that the sigma row of m is just this sort of characteristic vector of m, and this is just telling us where sigma maps I to. So if sigma maps I to j, I get a 1, otherwise I get a 0. That's exactly a perfect matching of Kn. So I'm doing some sort of something weird like that. Right? Okay, so this is this perfect matchings polytope, and now Birkhoff's theorem says that P is exactly the set of all vectors x in R2. Now, well, so just do something inelegant like that, of this proper dimension, such that each x sub this is going to get annoying. Oh, right, it's ij. Good. X of ij is greater than or equal to 0. And I also get a degree condition, which is going to be now impossible to write down that I've changed my notation. So my degree condition says that x of delta of each vertex in this graph is equal to 1. That means I get kind of sum 1 on every one of these vertices. Well, equality constraints. So this is nice. Why is it nice? Well, it tells me exactly what the facets of this polytope are. The facets of this polytope are exactly the faces I get when I choose one of these inequalities and set it to an equality. And of course, that's exactly going to be giving me a face when I look at a characteristic vector for my Coke-League. That was very quick. Well, let's write it down. I'll shortchange myself at the end. So I have m sub sigma such that sigma is in S, and m sub sigma such that sigma is not in S. These are the faces I get from this fact here. When I take the maximum and minimum values using my characteristic vector, I'm getting exactly the permutations in S and the permutations not in S. And each of these sets is a face, so it's contained in a facet. If we focus on this one, so this face is contained in a facet, i.e. Contained, if I set this to be F, F is a subset of the set of all permutations sigma, such that sigma of I is equal to J. These are what my facets are. And now it's just a counting argument. So now I just notice that, well, the number of vertices in this facet happens to be exactly the same as the number of vertices in this face. And now I'm done. This face must be that facet, which means the other face is described exactly how we want it to be described. And that is the EKR theorem for elements of the symmetric group. So in my abstract and title initially, I mentioned eigenpolytopes, and they're sort of hiding in here. So we use this polytope P, and I constructed P using the rows of this matrix M, where the columns were the characteristic vectors of these maximum Coke-Leagues. Instead, if I kind of shift everything by by subtracting 1 on n times the all ones vector, I can shift this polytope around. It doesn't change its combinatorial structure. It doesn't change its face structure, its face lattice. Now I have that this same matrix M that's giving me the vertices of this polytope has as its columns all of the tau eigenvectors I get from my canonical Coke-Leagues. So in general, if you have a graph, and there can be any graph at all, you can look at, so the theta eigenpolytope of X is the convex hull of the rows of any matrix whose columns are a basis for the theta eigenspace. Now you might start complaining because you'll notice that the polytope P that we were using, even in its shifted form, doesn't satisfy this definition, but if you trust me and maybe ignore the fact that I just drew your attention to that, we'll get on just fine. So the face structure is the same. Even if I construct my polytope in that way, it just lives in a space of a different dimension, which is fine. So some very nice thing about these eigenpolytopes is their face structure corresponds to equitable partitions, and I'm completely out of time. So I'll just mention that if you have a graph that's distance regular, and it just so happens that the graph that we're looking at is distance regular, then anytime you have an equitable partition in your graph, it corresponds to a direction in this kind of space where if here's my polytope and I look at some direction, I can kind of think of slicing this polytope into level sets corresponding to where the hyperplane orthogonal to this vector touches a vertex of my polytope. That gives me a partition of the vertices of the polytope. And sort of if if the partition of my vertices is equitable, then it's going to correspond to some direction for some polytope of my graph. And vice versa, if I have any polytope and I look at one of these partitions via direction, I get an equitable partition of the vertices of my graph. And that's exactly what we were using. So both of the characterizations of max Koch-Leaks sort of imply that when you have a graph where you have max Koch-Leaks that meet the ratio bound or the Kleek-Koch-Leak bound, and you look at the partition into the Koch-Leak and its complement, you're looking at a partition that's equitable. And that gives you quite a lot of structure you can play with. But I'll stop talking now, and if you have other questions, I'm happy to keep talking. But I'll let you go.